This slide deals with region of convergence of finite sequence. For example, if x of n is a finite sequence and the sequence is starting from here, n equals to 0, so we are talking about a causal sequence in this example, and 1, 2, 3 followed by a host of 0 after that. So it is finite because we're not interested in the 0, we're only going to examine 1, 2, 3. Then what happened? Or we should say, why are we not interested in the 0? Simply because 0 multiplied by z minus n is still 0. So adding 0 terms is not important in a series. So when we take the z transform of x of n, therefore in this particular example, we are only interested in the index from n equals to 0 to 2. Let's substitute x0, x1, x2, x0, x1, and x2, as well as the z here. So this is a finite sequence with only 3 terms for the series. The question to ask is, what is the value of z such that this sum converges? And you can try to put any z. And the answer is that almost any z, except z equals to 0, the sum would converge. Why so? Well, 2z minus 1 is equals to 2 over z. So, if z is equals to 0, then 2 over 0 is infinity, and the sum would not converge. So the answer is that the sum will converge for any z except z equals to 0. Right, let's see the picture on the right hand side. On the right hand side, this is the sequence we are talking about, a finite causal sequence existing on the right hand side. For the region of convergence, typically we use the shaded region, and this is the shaded region. This is the real part of z, and this is the imaginary part of z. And the answer is that we can shade everywhere on the z plane except at the origin. So the answer is the entire z plane except z equals to 0 for ROC of causal finite sequence. We now continue the discussion for finite anti-causal sequence. What is finite anti-causal sequence is here. The sequence exists from negative time, minus 1, minus 2, minus 3, and 0 after that. Well, so this is a finite sequence, and in the finite sequence, where for a bilateral z transform, where would it exist? So let's write the answer first. X of z is equals to, let the sequence be 1, 0.8, 0.6, and 0.4 followed by the rest 0. So the answer is summation of x of n, z minus n from n equals to minus 3 to 0. Right, so I write down for this sequence, this is the z transform. So you realize that we now have a finite series, all these terms. And for any z, as long as it's not infinity, we can add it up. Except, of course, when z equals to infinity. So the answer is for finite left-sided or anti-causal sequence, the entire z plane is the region of convergence except when z equals to infinity. What about the last example? In this example, we again have a finite sequence, but it extends from minus 3 index to 3 index. Only 7 numbers. When we write the equation for these 7 numbers, the sum is only from minus 3 to 3, xn z minus n. So as long as z is not infinity, or z minus n is not infinity, then the sum will converge. And this will occur only when z equals to 0 or z equals to infinity, will z minus n be infinity. Hence, the answer is the region of convergence is the entire z-plane except at these 2 points. So the take-home message is that for causal sequence, z transform always exists, with the possibility of at z equals to 0 or z equals to infinity. So the proof is on this page. Right, sorry, for this page we are talking about infinite sequence now. So for infinite sequence, let's begin with the bilateral z transform again. And the first idea is that we're going to take the absolute value, and we're saying that the absolute value of this sum is less than or equals to absolute value of, by taking the absolute value of xn multiplied by absolute value of z minus n, where we break z is equals to r e j omega, and n is here, minus, we can ignore e j omega n because that has a amplitude of 1. So the answer is that this sum is dependent on the sequence, absolute value of the sequence xn multiplied by r to the power of minus n. We now can choose different r, and in the past example we have realized that for certain large value of r, for causal sequence, infinite causal sequence, then the sum would be absolutely summable. Let's now examine causal sequence, causal infinite sequence. Here we have a sequence that only exists on the right hand side, so it's causal and it progresses to infinity, doesn't die. We have shown you in the past example that the region of convergence is external to some position outside a certain pole. Later on you'll realize that it is the pole that is furthest away from the origin, if there is more than one pole. If there is only one pole, it will be that pole position determining the radius r1. If there are more than one pole, it is the pole position of the furthest one away from the origin. So how do we understand that the region of convergence is external? It's because for causal sequence, as n becomes larger, r to the power of minus n becomes smaller. When we say when we have a value of r and r is becoming larger, then z to the power of minus n becomes even larger. So if we choose a r here versus r here versus an r here, so we have r1, r2 or r3, where this r is the distance to the origin. The larger the r, so r3 minus n is less than r2 minus n is less than r1 minus n, as n tends to infinity, positive. Since this value is being used in the denominator, therefore xn times z minus n tends to 0. Faster for those r's that are even further away from the origin. Hence we see that the region of convergence is actually outside of a ring, and the position of the ring is at the smallest, is at the ring encircled at the point of the furthest pole from the origin. Now what about infinite sequence that is anti-causal, which is this case over here? In this particular case, you realize that as n tends to negative infinity, then x of z, which is equals to, let's say, from n equals to 0 to negative infinity, x of n z minus n, we have this equation. Now for the denominator term to tend to infinity, z to the power of we have negative n here. So what happened is that we need z to have smaller and smaller value. And when z have smaller and smaller value, z minus n becomes larger and larger. And hence the region of convergence is inside actually it will be inside the smallest, the pole that is nearest to the origin if there is multiple pole. So compared to the right-sided causal sequence, in the causal sequence, the region of convergence is external to something, the pole position. While in the anti-causal signal, the region of convergence is inside a ring. So to conclude, if we have a two-sided sequence, both that extends from negative infinity to infinity, then this condition may happen. That means we have a ring like this. However, please be careful. If it is possible that this ring does not exist, there is no shaded regions representing a region of convergence, when that happens, we can say that this signal is not Z transformable, does not exist. Now, you can try for this signal. A signal that is just not a unit step. A unit step only exists on the right. So it is a constant existing from n equals to negative infinity to positive infinity. And you realize that actually this signal has no Z transform. However, of course, in most cases, in practical cases, we are ignoring the anti-causal part and saying that when n is less than 0, then we are examining whether this signal, which is the step function, is Z transformable or not. And in this case, of course, it exists. So pay attention to these two slides. This is the slide showing the the region of convergence for infinite sequence. On the top is for causal sequence, in the middle is for anti-causal sequence, and on the bottom is for two-sided sequence. Thank you.